Hello everyone, this is Engineer Selassie from Hello Academy and Brain Boosters, and today we are going to see chapter 17. This is free space management, and let's get into it. So as you can see, free space management, free space must be managed to avoid fragmentation. Easy if free space are in the fixed size using paging. Hard when free space are in variable size if using segmentation, for example. So segmentation suffers from external fragmentation. What is external fragmentation and what is internal fragmentation? We will discuss. So fragmentation means external fragmentation, the free space gets chopped into little pieces of different size and is then fragmented. Subsequent request may fail because there is no single contiguous space that can satisfy the request, even though the total amount of free space exceeds the size of the request. So, for example, in your memory, let's see this one. For example, we have 30 bytes of heap. This is our heap. We have free 10 bytes here, and 10 is used, and another 10 is free. So the total free we have is 20, but the requested 15 GB at one location we don't have 15 bytes. So because of this we cannot accommodate this request. This is an example of external fragmentation. Internal fragmentation, if an allocator hand out chunk of memory bigger than the requested. For example, if you request 15 and if you had memory space, if the allocator gives you 20 bytes, then that will be internal fragmentation. Okay, and thus unused space in such a chunk is considered internal fragmentation because the waste occurs inside the allocated unit and is another example of space waste. So we have external fragmentation and we have internal fragmentation. So in our space management we have this problem. So assumptions to check, to see the assumptions in order to understand the different mechanisms of memory management. The first assumption we will see is focus is on user level memory allocation libraries like malloc and free, and interface for malloc and free, and we have void, and as you can see the syntax is malloc size t and we have size here, and we have void. This is for free. If you have a pointer then to free we use this syntax. We focus on solving external fragmentation. We don't care, we don't consider internal fragmentation here. Once memory from free list is allocated to a requester or the client, it cannot be relocated to another location. This is also one assumption. Once it is allocated, we cannot relocate it into another location. Okay. No compaction of memory in free space. The memory being managed by the allocator is of fixed size and contiguous. These are the assumptions we are going to follow. So as you can see, we have assumptions in order to understand. So low level mechanisms, memory management. The first one is splitting and coalescing, and the second one is tracking the size of allocated region, and the third one is building a simple list inside the free space to keep track free space. These are the three methods. Let's see one by one. The first method is splitting. For example, finding a free chunk of memory that can satisfy the request and splitting it into two. For example, when the request for memory allocation is smaller than the size of the free chunk. As you can see here, we have 30 bytes of heap, and we have from 0 to 10 bytes we have free, from 10 to 20 we have free, from 20 to 30 we have free. Okay, the used is the middle one. So if you see the free list, we have head, and address from 0 to 10 is free, from address 20 to 30 is also free. So we have 20 and the length is 10. So this is the free list. Now, two 10 bytes free segments, we have two 10 bytes free segments. But for example, if you are requesting only one byte, so what we are going to use splitting 10 bytes free segment. So what it does will be, as you can see, from 20 to 21, 1 byte will be allocated to the pointer, the requester, and if it is the operating system can choose this one or this one. For now, let's assume we choose this part. So as you can see, the address now, free address will be from 21 until 9. Now the length will be 9. So this is a free list. This is a splitting technique. The second is coalescing. Okay, coalescing. If a user requests memory that is bigger than free chunk size, the list will not find such a free chunk. Okay, coalescing merge returning a free chunk with existing chunk into a large single free chunk if address of them are nearby. So what it does is, let's assume that the middle one was freed. Now we have this heap location, okay, heap address. So what coalescing does is it will merge all of them into one heap memory. So this is coalescing technique. The third method, tracking the size of allocated region. Okay, this one, the interface to free, as you all know, we have void and we have the pointer. Okay, does not take a single size parameter, because when we free, we don't use any size parameter. Why? How does the library know the size of the memory region that will be back into free list? Because we simply free the pointer at that location. So there should be something, because if we don't give the size, how this free API freed the size? The answer is, most allocators store extra information in the header block. As you can see, for example, if we have a pointer in malloc 20, then we always have all allocated region, okay, unallocated region plus header. We have an header. As you can see, the pointer is here. The total requested area, the return to the caller is 20 byte, because 20 byte is what we requested. But in addition to the 20 byte, the header used by malloc library will be attached to the pointer. This is magic, because we're going to have the size and the magic number. So the header of allocated memory chunk, the header minimally contains the size of the allocated memory region. Okay, so the header will have its own memory, most of the time 8 bits. Okay, the header may also contain additional pointer to speed up the allocation. A magic number for integrity check. As you can see, we have a magic number here, and we have the size also. And as you can see, header pointer will be assigned here, and this is a requested pointer, 20 bytes, and the specific content of the header will be like this. So if you see the simple code, this is a code type defined structure, header T. So in the header T we have the size and the magic number. So this will be the header pointer, a simple header code is like this. So when you run this, it will create the header of the requested memory. So the size for free region is the size of the header plus the size of the space allocated to the user. This is very important. So whenever we request for a memory, the header size will be attached. Most of the time it is 8 bytes. If a user requests n byte, the library searches for a free chunk of size n plus the size of the header. In this scenario, the size of the header is 8 byte. Simple pointer arithmetic to find the header pointer. So to find the header pointer, we make a simple calculation. What we do, this is the code void free, this is the pointer, then header, the header pointer is equal to pointer, the requested pointer minus the size of the header. Then this will give us allocation of the pointer. Embedding a free list. So the memory allocation library initializes the heap and puts the first element of the first list in the free space. So the library can't use malloc to build a list within itself. Okay. So the memory allocation library initializes the heap and puts the first element of the first line in the free space. So this is very important. The library cannot use malloc to build a list within itself. So this one is embedding a list. The first thing what we do is description of the node of the list. So what we do, type definition structure node, then int size structure node t, and next this is node underscore t. This is the first instruction. Building heap and putting a free list. Assume that the heap is built via mmap system call. So what we does is just simply run this code mmap, return a pointer to a chunk of free space. So what we are going to do, the header pointer is here, mmap null. So in this situation we need 4 GB, and as you can see we have map private, and the header size is 4096, then return this next null. When we run this code, what we are going to get is a heap within one free chunk. Okay, so this will be created. As you can see, return a pointer to a chunk of free space. So here when we run this 4096, this is the size of the memory we requested, but as you can see here the size is 4088. This one is because we subtract the size of the header. Okay, the size of the header is 8 byte. So the virtual address is 16 kilobyte and the total address is 4096 bytes. So 4096 minus 8, it will be 4088 byte. So as you can see, this is created. Now the size is 4088. This is the header, and the rest of the 4 kilobyte chunk is here. Okay, 4088 header. Next field null is 0. So this will be created. Now we don't assign anything. This will be the heap size. Now embedding a free list allocation. If a chunk of memory is requested, the library will first find a chunk that is large enough to accommodate the request. This is simple. The library will split the large free chunk into two, one for the request and the remaining free chunk. Shrink the size of the free chunk in the list. So let's see now. For example, embedding a free list allocation. Example, a request for 100 bytes of bytes by pointer malloc 100 was requested. So allocating 108, don't forget 100 is for the request and 8 is for the header. Okay, so allocating 108 bytes out of the existing one free chunk, 8 bytes for the header. So what we are going to shrinking the one from free chunk to 3980, because we have 4088 minus the request is 100, the header is 8 minus 108. Now we have 3980 bytes of free space. So we are assigning here 100 bytes new allocation. The pointer will show us here, the magic number is here, the size is here. So now our heap looks like this. Free space with chunk allocated. So if you see here, now we allocate 1, 2, 3, 8 bytes. Okay, so the final free space we are gonna left is 3764 bytes of chunk, because you simply 4088 and minus 3 times the header. Okay, 1, 2, 3. So 3 times 108, it will give us 3764 byte of chunk. So as you can see, when we allocate the pointer and the header the header byte is 8 bytes. So this is how we allocate the memory in the heap. So as you can see, the final heap size is 3764 bytes of chunk is free now. Now how to free space? Free space with free API. Example, free SPTR. SPTR means here, for example, in the middle one, we are going to freeze this 100 bytes of location in the memory. So what we are going to do, equivalent to free 16,500. Okay, this is the location. How this 6,500 comes, we will see. At the top we have 16 kilobytes of heap. So 16 kilobytes means 16,384 bytes. This is the beginning of the virtual address. Then we have 8 bytes. Okay, we have 8 bytes of header and 100 bytes of allocated, so 108, and plus this header 8. So the location is 16,500. As you can see, 16,500, that is the location. So what it does is the 100 byte chunk is back into the free list. From here, this one will point to here, and the location of this one will be 16,500, and this will be now a free chunk of memory. So the free will be 3,764 bytes of chunk, because 100 is returned. The list header will point the small chunk. Now as you can see, the list, it will show the header of the free chunk. The same is true, free space with free chunk. Let's assume that the last two in-use chunks are freed as well. So extra, what it does is this one, as you can see, this will show here, and this one will show here, and this one will show here. So everything is freed now. What is the problem? The problem is external fragmentation occur, because we have full memory but in different locations. So this is not advisable in the memory management system. So coalescing is needed in this case. So by coalescing, we have to find one full monolithic memory. So growing the heap. What if we need additional memory size? So how grow the heap? Most allocators start with a small size heap and then request more memory from the operating system when they run out of memory. So this is the two command, sbreak and break. In most Unix system, we are using these two commands. So let's say this is not in use, we have heap not in use. So as you can see, our heap is here. So if we need, this is address space. So we have a break here. So if we need additional memory, we use sbreak. So we're gonna request and get the additional memory size here. This is in the address space. But as you can see, when we map the address space, the virtual memory into the physical memory, the location might not be in the same location. The operating system may give different address location in the physical memory. So as you can see, this heap might be here and this one might be here. So this should be noted. Managing free space basic strategies. we have a lot of strategies how to manage the free space. The ideal allocator is both fast and minimize fragmentation. This is ideal. So the first one is best fit method. The best fit method, what it does is finding free chunks that are big or bigger than the request, returning the one of smallest in the chunk in the group of the candidate, because it will find every chunk which is greater than the requested memory size, but it will give the smallest. The opposite of best fit is worst fit. This is finding the largest free chunk and allocate the amount of the request. So this will assign the largest free chunk and allocate the amount of the request, keeping the remaining chunk on the free list. This is the worst fit. The first fit, finding the first chunk that is big enough for the request and no need to travel all the memory address. Once in the first comes and it found any big enough memory location, then it will assign it, returning the requested amount and remaining the rest of the chunk. Next fit, finding the first chunk that is big enough for the request. This is the next fit. So searching at where one was looking at instead of the beginning of the list. So let's see an example of basic strategies. Let's say allocation request of size 15 byte was requested. As you can see, our heap size is 10, 30 and 20. So in the case of result of best fit, what it does is 15 byte is less than 30 byte and 20 byte. So from 30 and 20 it will choose 20 because 20 is the smallest, and it will give 15 byte for the request malloc 15 byte, and the free list will be 5. A result of worst fit, we are requesting 15 byte. As you can see, 30 and 20, but from both 30 and 20, 30 is the biggest, so it will give 15 byte for the first and 15 byte will be in the free list. Other approach, for example, segregated list. Segregated list means keep dedicated list for popular request size. Others are served by the general memory allocator. Example, kernel data structure such as logs, inodes, etc. So it's already a pre-list, dedicated list. So the problem is new complication. How much memory should dedicate to the pool of memory that serve a specialized request of a given size is a problem. That is a problem in this situation. So slab allocator handles this issue. The solution is to use a slab allocator. So what is a slab allocator? A slab allocator is allocate a number of objects in the cache. So the objects are likely to be requested frequently. Example, logs, file systems, inodes, etc. Request some memory from a more general memory allocator when a given cache is running low on free space. Now the other one is body allocation. Binary body allocation optimized for coalescing. Coalescing, what it does is when a request is made, search for free space by recursively dividing the total space size power of 2 until a block that is big enough is found. So the allocator divides free space by 2 until a block that is big enough to accommodate the request is found. For example, if you have 64 kilobytes of memory, then it will divide it into 32 kilobyte, then 32 kilobyte will be 16 kilobyte, then 16 kilobyte will be 8 kilobyte. As you can see, we request 7 kilobyte, so it will be here. But the problem is we're gonna face internal fragmentation problem. Other approach, body allocation can suffer from internal fragmentation. As you can see, we request 7, but it is allocated 8. but the system makes coalescing simple, coalescing two blocks into the next block of blocks. Other approach use more advanced data structure to address scaling and multiprocessing systems. So as you can see, we have seen a lot of approach, but the allocations and segregated list, and basic strategies like best fit, worst fit, next fit, first fit. These are basic free space management strategies. How to draw the heap using break API, and how to free. We have seen here freeing a heap. We're gonna experience a problem, external fragmentation and free space with free. We have seen that, and the idea of header, and the size of the header is 8 kilobyte, and embedding a list, how to split and shrink, and the other embedding free list as well, and the header of allocated memory chunk, and tracking the size of allocated size. As you can see, we have header here, and what is coalescing, what is splitting, and the assumption memory management. Everything is discussed, and so chapter 17 was in a nutshell like this, and we shall meet in the next chapter. Thank you for your time. I hope this video was helpful for you. Thank you so much. Thank you. Bye bye.